to make room for the barbecue lunch. So I'm going to spend maybe 20 minutes. I want to give an example using the spectral sequences from yesterday. And then Sasha's going to do something with the rest of the hour, some more examples, some more filling in things that this lecture is sort of the overflow lecture from what's come earlier. So he didn't call it by this name, but yesterday you had this, it's called the Grothendieck spectral, well, it's one form of the Grothendieck spectral sequence. Which is if I have I have a complex E, and it's RQ. So E is going to be a complex, and F is going to be a left exact functor. RQF, so the E1 page is RQF of EP, and this converges to RP plus QF of E. And I'm going to remind you what all that means, and I'm going to use it in an interesting example. I'm going to use it to compute the cohomology of a complete intersection. And maybe I'll just recall for you the cohomology of line bundles on P4. I mean, you could do anything, but I'm going to do P4. And which ones do I need? I need, so here we have O of 1, O of 2. And I'm going to need quite a few negative ones. O minus 1, O minus 2. I'll just put this up for reference. I'll probably need more than these, but this is enough for now. So I want to write down the dimensions, and I want to think of H0 as being at the bottom. H0, so little h0 just stands for the dimension of big H0. H1, H2, that's more space. Just to remind you what this looks like, so you know O is the sheaf of functions. It has one section and no higher cohomology. And O of 1, its sections are the linear forms on P4, linear forms in 5 variables, so there are 5 of those. And O of 2, its sections are quadratic forms in 5 variables. So I need, what is it? 5 plus 2 choose 2 is 7 choose 2 is 21, yeah? And no higher cohomology. And then O of 3 is 5 plus 3 choose 3. That's 8 choose 3. That's 56. I need your help to not get these numbers wrong. Yeah, I've already got the numbers wrong. This should be a 4. What is 6 choose 2? 15. And 7 choose 3 should be 35. Yeah, okay, these already look more like the numbers I had prepared. Okay, then you know O minus 4 is the canonical, or sorry, O minus 5. Oh, I do need to go one more to the I need O minus 6 there, or we're going to lose our minds. It's really the negative ones that we need. So O minus 1 has no sections. Well, the negative ones all have no sections. O minus 5, this is the canonical bundle of P4. So its cohomology looks like the cohomology of O upside down. That's Serre duality. And the cohomology of O minus 6 looks like the cohomology of O of 1 upside down. That's Serre duality. Right, and then O minus 7, you're going to have a 15 and then a 35, and you get the idea. And in between, these ones have no cohomology. It's nice to see this all in one place, I think. Okay. So now that we have that, don't let me erase that. If I start to erase it, you stop. And so what I really want to talk about is X is going to be an intersection. It's going to be a quadric intersected with a cubic in P4. So this is, and I want it to be smooth. And I want the cubic not to be the union of I want it to be two-dimensional. I want it to be a smooth, proper intersection. It's going to be a surface. And I want to compute its cohomology. HPQ of X, which is going to be, which is I'm going to be over C. So I want to compute these numbers, the Hodge numbers. And I'm going to put them together in a Hodge diamond like this. So first, I want to compute the cohomology of OX. So to get the cohomology of OX, I'm going to use this Koszul resolution. And let's say that my quadric is given by a quadratic form Q of x naught up to x4, and my cubic is some f of x naught up to x4. So Q is a section of O of 2. And F is a section of O of 3 on P4. And so I have this map from OP4 to OX, which is surjective. And the ideal sheaf of X is just generated by Q and F. And so this kernel is given by the map from O minus 3 plus O minus 2. This is given by F and Q. And then this is a Koszul complex. And so I have, next I need to put Q and minus F here. And what needs to go here is OP4 of minus 5. And because X has the expected dimension, this complex is exact, because X is. And now, so I know the cohomology of these line bundles on P4. I want to compute the cohomology of OX. And of course, you could, if you just learned about cohomology, you might say, well, let me split this into two short exact sequences. So here I'll put IX, right? So now this is a short exact sequence, and this is a short exact sequence. and I'll do the long exact sequence in cohomology twice, and I'll paste all the information together and get the answer. And indeed, you could do that. But whenever you find yourself doing that, secretly you're doing the Grothendieck spectral sequence, and you didn't know it. Let me rephrase this exact sequence as saying that that OX is quasi-isomorphic to the complex OP of -5 goes to O of -3 plus O minus 2 goes to O, with this one in degree 0. Right. This complex is quasi-isomorphic to OX. And so I want to compute cohomology of OX, right? So, or in other words, Ri gamma of OX for all I. Right? And I know the cohomology of the terms of this spectral sequence. So how do I use it? So this way is going to be P, and this way is going to be Q. P can be 0, 1, or 2. Or sorry, excuse me. P can be 0, -1, or -2. Maybe you want me to put the Q axis on the other side. Maybe you'll be happy about that. And we're on P4. So we could go as high as 4. So let's take cohomology of, and I'm just going to write the dimensions of these cohomology groups. So the cohomology of O is here, 1, 0, 0, 0, 0. The cohomology of this thing is 0, 0, 0, 0, 0. And the cohomology of this thing is 0, 0, 0, 0, 1. Can I take, maybe I should take questions, because if you fall off the horse, this becomes very boring. Questions about what we're doing?
So is this the first page or is it?
Yeah, this is the E1 page. This is, and it goes this way. So you see there are no differentials. I'm going to take kernel mod image to get to the next page, but all the differentials are 0 because there's just nowhere for them to go. And so then you go now to the E2 page, and the differentials are like this. Right? And again, there's nowhere for them to go. Right? There's nothing hitting. So we're going in a night move, right? And then you go to the E3 page, and again, there's nowhere for the differentials to go. I'll just leave this here. When you go to the E3 page, then the differentials will be even farther off the map. And so there's just nowhere for them to go. And so the thing degenerates. And now what it tells you is that, so on this diagonal here, this diagonal gives me a filtration that computes H0 of OX. And this diagonal, where P plus Q is 1, gives me a filtration that computes H1 of OX. And this one, I missed. Sorry. Let me draw that right. So this diagonal computes H0. This diagonal computes H1. This diagonal computes H2. So without chopping this thing into long exact sequences, without chopping this long exact sequence into short exact sequences, we've found that the cohomology of OX is 1, 0, and 1. And so here, in the Hodge diamond, I can put 1, 0, and 1. And by Serre duality, I can put also 1, 0, and 1 there. Okay. Now we also need to compute the cohomology. We'll need to compute the cohomology of OX of -1 and OX of -2 and OX of -3. So let's do that. By the way, you may be disappointed. You were hoping for some excitement with boundary maps and things changing from one page to another. But if you have some experience with spectral sequences, you know your dream is that there are just no boundary maps, and no, like you want as many zeros as possible. Right. So let me recycle this same drawing. Now to do the cohomology of OX of -1. So if I twist all these by -1, then I'll have here -6, -4, -3, -1. Sorry, Sasha, this is going to take half an hour. Yeah. So what's the cohomology of Pn there? So cohomology of OP4 of -1, we look, is 0. Cohomology of this thing is also 0. And the cohomology of O -6 is there. I get 0, 0, 0, 0, 5. So again, looking, I find that H0 is 0. Well, so this is already, there's nowhere at all for the boundary maps to go. And so I find that this must be 0, 0, and 5. This is for questions about that? So the next one is going to be more interesting. Yeah, so I'm computing the cohomology of these line bundles because when I go to do the cotangent bundle, I need all these. And also, for whatever reason, I don't want to assume that I'm over C, so I can just flip this from left to right. There are many other ways to find these Hodge numbers, of course. But this shows you how to use this sequence. Let's do OX of -2. So now something new is going to happen. So here I have -7, -6, no, sorry, -5, -4, and -2. So the cohomology of OP -2 is all 0. Cohomology of O -4 is 0, but the cohomology of O -5 is 1 at the top. And the cohomology of O -7 is going to be 15 at the top. this is to compute cohomology of OX minus 2. So now finally something interesting is happening. We have this boundary map here. And so this boundary map could be 0, or it could be surjective. And well, let's see. If it's, where's a good place to work? If it's 0, then the E2 page will look like this. So if this map is 0, then the E2 page, I'll take kernel mod image won't change anything. Right. And now I have boundary maps like this. And so now it's degenerate. Right now I can run to the end and nothing more will change. And so from here, I will find, here will be H0 of OX of minus 2. Here will be H1. Here will be H2. And here will be H3. But what's wrong with this? X is a surface. So this is we can't have some H3. So again, I don't actually have to know very much about this boundary map. This boundary map has to be a surjection. Otherwise, we would end up with H3 of O minus 2. So instead, the E2 page had to look like a bunch of zeros here, zeros there, and a 14 here. And so now looking at its cohomology, you see this had to be a 14. And this one, similarly, is going to be, if I'm not making a mistake, if I put minus 8 there, I'll have 35. Minus 6, I'll have 5. Minus 5, I'll have 1. I believe this is 19. Sorry, let me just double check a little bit better. No, sorry, 29. So you play the same game with O minus 3, and you'll get 29 here, if I'm not making a mistake. Questions? So you can compute with the adjunction formula, by the way, that omega x is, well, it's OX of minus 5 because we were in P4, plus 3 plus 2 because we were the intersection of a cubic and a quadric, which is OX. So cohomology of O minus T is H2 minus I of O of plus T by Serre duality. And so you could also compute, you could also twist this sequence the other way. You could compute the cohomology of OX of 1, OX of 2, OX of 3, and you have an exercise to do that using the same spectral sequence, so you could get a taste of it. And now what are we going to do for the cohomology of omega x? Cohomology of omega x. Well, first of all, we have the normal sequence. So the tangent bundle of x embeds in the tangent bundle of P4 restricted to x. And the normal bundle is O of 2 plus O of 3. Because x is cut out by a transverse section of this vector bundle, given by Q and F. And either you know or you go read, that means that the normal bundle is, this is OX of 2 plus OX of 3. This map is essentially the derivative of Q and F. Or if we run it the other way, because we're interested in the cotangent bundle, to omega P4 to omega x. Boy, this is really okay. We have to keep this. And we also, to compute the cohomology of omega x, right. So omega x that we're interested in is isomorphic to this two-term complex right here, quasi-isomorphic. But to compute the cohomology of this thing, omega P4 restricted to x, we also need the Euler sequence. Omega 1 P4 goes to O of minus 1 to the 5 goes to O. So omega 1 P4 is isomorphic to this complex of things whose cohomology that we know. I think actually it's okay for me to use this board now. Gotten everything we need out of there. So the upshot, I want to say that the cotangent bundle of x is quasi-isomorphic to this three-term complex. OX of minus 3 plus OX of minus 2 goes to OX of minus 1 to the 5th goes to OX, where this is in degree 0. Right? So if you like, the kernel of this map is omega 1 P4 restricted to x. And then the kernel of this mod the image of this is omega x. Questions about that? Should I say more? Again, kernel mod image. To understand the kernel, you look here. And to understand that, right, this kernel mod this image, you look here. Okay, so now we want to use the Grothendieck spectral sequence again. So here's our p direction, and here's our q direction. So I should put the cohomology of these three terms going up. So I get 1, 0, 1, looking up there. I get 0, 0, 5 times 5 is 25. And I get 0, 0, 14 plus 29, help me save me, 43, thank you. And again, I have some interesting boundary maps. Right? And now, knowing, well, let's see. This diagonal at the end is going to give me h0 of omega x, and this one's going to give me h1, and this one's going to give me h2, and this one's going to give me h3. So this map must be surjective. Right? Otherwise, that 1 will survive to the E infinity page of the spectral sequence and give me h3 of omega x. Right, this is of omega x, which shouldn't happen. But this 25, well, OK, so it has to surject, so there will be a 24. But the rank of this map, I can't tell by that similar trick. But I can tell, I'm never going to get anything on this diagonal. Right? So h0 of omega x is 0. And by Serre duality, I know that h2 of omega x is 0. So maybe here's an exercise. See how whatever we said about Serre duality in the last hour implies that on a surface, this vector, this dimension and that dimension are the same. These two vector spaces are dual to one another. Right? If you're not used to Serre duality, that may look different from what we said, but you should understand why those are the same. So this has to go away, right? And so h1 of omega x. Well, now I can just take it. Now I can just take an Euler characteristic, right? H1 is going to have to come from. It's going to be 43 plus 1 minus 25 plus 1. However, these things end up interacting in the middle, at the end, I know I'm going to get 0 here, and so I can just take Euler characteristics. And if I haven't made a terrible mistake, this should be 20. So I have but I could see from the spectral sequence that h0 of omega x vanished, and that gave me enough to finish. So of course, this is a K3 surface. There were many other ways to see that, but the point was you have some object whose cohomology you want to compute. You resolve it by things whose cohomology you know. The spectral sequence takes care of the bookkeeping that you would have done to chop that up into many short exact sequences. And hopefully, you have enough information that you don't have to think hard about the boundary maps. Tomorrow, we'll see another fancy example along this way. And now, Sasha's going to talk for a bit. Yes.
Okay, so I'll start by saying a few more things about Serre duality, and then we'll talk about other things. So it's just sort of various things that we either forgot or didn't have time to mention in the last couple of days. So let me return to this situation where we have homomorphism, and you have the corresponding local isomorphism of local version of adjunction between f. So we have corresponding push forward functor, and we have the right adjoint to it, which we constructed. So f upper Schrick of something is you take the pullback tensor with omega f by difference of dimension. So in fact, from this formula, you see that what you have here, this is actually f upper shrik of O. Right, and so then the kind of version of Serre duality, it's called relative Serre duality or Grothendieck duality. So this tells you that when you take R home from R f star f G, this is isomorphic to R f star R home f to upper shrik G. So a few more remarks about this. So in the case when you take G to be O, so then this becomes some kind of version. You should think of this as a relative version of Serre duality. So the statement would be the following. So the left-hand side becomes R home from this guy to O. So this we should think as dual. So we take R f star f, and then we kind of take dual of this. So R home to O. So this is isomorphic to RF star. And here we take R home from F to F upper shrik of O, which is this guy. So it's omega F shifted by the dimension. So in the case when y is a point, then this says the following. So the left-hand side becomes R gamma of f. And then we just take dual of this as a vector space or graded vector space, right? And on the right-hand side, it will be R gamma over x. Here we have R gamma x. And here we take R home from, well, the same thing, R home from F to this guy. So this becomes the, well, especially if V is F is a, for example, vector bundle, this becomes the usual Serre duality when we pass to cohomology. And so this can be thought of as a relative version of this. So if x to y is, for example, some smooth morphism, so we can think of the push forward as somehow taking cohomology in the fibers. So this is the relative analog of the sheaf of differentials. So this really should be thought as an analog of Serre duality. However, there is one important difference between this isomorphism and this isomorphism. So this isomorphism is happening in the derived category of a point, so just derived category of vector spaces. So here, this isomorphism is equivalent to just isomorphism on every cohomology. So I pass to cohomology, and I get the usual isomorphism between hi of this and n minus I of this, of something else. So it's equivalent to, well, with dual here. So on the in the case when this is, we're talking about isomorphism on y, where y is some variety, then we cannot actually separately we do not have separately duality between if we take just ith derived functor of the push forward and then take dual, we will not have a similar relation to some other ith derived functor. And actually, I can illustrate this with the following example, which is actually the example Nick considered yesterday, where you have a line bundle over a square of elliptic curve. Yeah, so this example is that illustrates that the relative Serre duality does not hold for individual high derived functors. So you only need to take this full derived functor, which is an object of derived category of y, and then the dual will behave correctly. So let's take E to be elliptic curve, and on this elliptic curve we have this line bundle L, which is O of delta minus P naught times E. And so we consider as morphism F, we consider projection to the second factor. This is F is projection to the second factor. So then we can apply, so also in this case, for elliptic curve, omega is trivial. So it is also going to be a trivial, the relative omega is also going to be trivial. So Serre duality just says something about connection between RF star L dual and RF star. So here I have to take the right-hand side will be R home from L to this guy. So it's just going to be L inverse. So the relative differentials are trivial in this case. So it will be just L inverse shifted by 1. Now, the computation that Nick was explaining last time, so this RF star L, it's actually 0. It's supported just at one point P naught. So, and in fact, so this complex RF star L, it always can be presented by a complex of vector bundles of degree sitting in degrees 0 and 1. This is can be seen using, for example, Czech resolutions to compute this. So when you just compute the usual, the zeroth cohomology of this complex. So this is kind of zeroth cohomology of this complex. So the complex is represented by some morphism of vector bundles. And so in particular, this H naught, this is a kernel of this. So it is a torsion-free sheaf. It's a subsheaf of a vector bundle. On the other hand, it's supported just at one point. So this implies that it's actually 0. On the other hand, the full derived functor is very much non-zero, and actually the same holds for the other guys. So f star of L inverse is also 0. But when you compute R1 f star for either of them, it's going to be non-zero. And in fact, I think Nick tried to explain it. It may be already explained that this is actually going to be O of pi P naught shifted by minus 1. And actually, this is true also for L inverse. So you see that even though we have such a duality, there is no duality between so in this example, there is no connection between so this one dual is not equal to R1 f star L inverse. because one side is 0 and the other side is not 0. So what happens is that both complexes are actually just concentrated in, they have cohomology in degree 1, both this and this complex have, well, without 1, they have cohomology in degree 1, and so the duality actually, so it says that when you dualize a thing like this, you get again this shift, but in a different, in a degree shifted by 1. So, so it just says that there is a x1 from OP0 to O is equal to O. So that's what, to OP0 again. So that's basically what this duality boils down to this kind of duality. But you cannot just kind of naively mimic the Serre duality that we have between cohomology. When we have a fibration, you can just try to replace cohomology by ith derived functor. So this turns out to be not correct, and that's maybe one of the ways, one of the reasons why it's not enough to just work with high derived functors. You actually have to consider the full derived functor here, which is a complex. Okay, so this is one thing I wanted to say. So now another remark is that there is a generalization. So the assumption that X were smooth and projective is not actually necessary. So there is a generalization of this. There is a generalization to the case to kind of general schemes. Well, maybe sufficiently nice schemes, but certainly there is no. It's not necessary to assume smoothness or anything like this. So the main point in this theory is that you have to replace bounded category of coherent sheaves. You have to replace it by unbounded category of quasi-coherent sheaves. And it turns out that it's better to work with this because it admits arbitrary infinite direct sums, so over any set. And so because of this, you can use general representability theorems. And so using kind of general representability theorems, one construct this right adjoint functor from unbounded derived category of quasi-coherent sheaves on Y to unbounded derived category of quasi-coherent sheaves on X. And this isomorphism still holds in the setup. However, what is not always true is, so it's much kind of harder to understand this functor F upper sheik. However, it is still true under very general assumptions. So we still have duality isomorphisms, and plus we still have so under very general assumptions, one has this isomorphism between F upper sheik of F and F upper star of F tensored with F upper sheik of O. So the major thing becomes understanding this F upper sheik of O. And yeah, well, this requires actually a little more. So before you even can ask the question about this adjoint functor, you first need to extend. So this push forward actually can be defined for unbounded complexes. So remember that we defined it. We defined derived functors only for bounded above or bounded below, depending on whether it's left exact or right. So this can be defined actually for all complexes without any conditions. But this requires some technical additional work. So one needs to work with resolutions of unbounded complexes. So anyway, so one consequence of this, which of course was also known classically, is that if you have a singular scheme which is not Well, on singular scheme, you still have some version of third duality, but instead of dualizing, instead of this omega x, you have to substitute some complex. So if x is possibly singular scheme, but projective scheme, so then still have version of third duality in the following way. So I need projectivity so that the cohomology are finite dimensional. So if you have some sheaf and you want to calculate hi of this sheaf on F, so the dual of this is going to be H. Well, maybe I'll write this in terms of R gamma. So it's going to be R gamma of R home from F to certain dualizing sheaf. Well, actually, certain complex. So maybe I'll call it D sub X. So this is just the following. So you have a projection from X to the point, and you just take P upper Schrick of structure sheaf of a point. So in general, this is a complex. So if X is smooth, then this will be what we had before. So, but it turns out that it's important to, so there is a lot of interesting connection between singularity of X and singularities of X and the structure of this complex. So for example, one known case. Yes, and also there is a kind of, there are ways of computing it which have to do with the fact that you can embed X into projective space. And so you can use the following observation that so just for very general reasons, because f Schrick is defined as an adjoint functor, we have this formula for compositions. So therefore, one immediately sees that if you have a morphism, then if you apply upper Schrick to this to the dualizing sheaf, you get a dualizing sheaf upstairs. So I can apply this to this morphism, and so we see that the dualizing sheaf of X is actually I upper Schrick of the dualizing sheaf on Pn. But dualizing sheaf on Pn is just what we had in the case of a smooth variety, so it's omega Pn shifted by n. And I upper Schrick for an embedding is actually not so hard to understand because it's defined. It actually can be defined as a derived functor of a certain functor between abelian categories. So, namely, if we apply this general duality in the case of the closed morphism, so if I from X to Y is a closed morphism, closed embedding, then this isomorphism says that, well, the corresponding functor is exact. That's the main point. And it also, when you need to know like some sheaf here, if you know it's pushed forward to Y, then you can recover the original sheaf from it. So there is a kind of abelian version of this functor I Schrick. So I Schrick is a derived functor of the following functor. So you take a sheaf on Y. So start with F, just coherent sheaf on Y, or quasi-coherent. And then you consider home from I lower star of OX to F. And So this is actually sheaf on Y, but you can see that this is I star of I upper I lower star of some sheaf on X. And so this sheaf on X is actually the kind of underived version of I apostrophe. So this is, unfortunately, it's also denoted as I apostrophe of F, but this is actually just underived version of this. So this is sheafified H naught of this. So if you want to pass to derived functor the whole I-sheaf, you have to replace this home by the derived version, and then you get precise formula which allows to calculate I apostrophe in this case. So in particular, it allows you to study the cases when the dualizing complex is actually concentrated in 1 degree. So if for example, if X is what is called Cohen-Macaulay, then so we choose embedding of X into projective space, and the dualizing sheaf of X is going to be so you take sheaf X from the structure sheaf of X viewed, well, yeah, maybe this is really I lower star of this. So to the dualizing sheaf of Pn, but we put here codimension. So this is C, which is the codimension of X. So if it's a hypersurface, then you just take X1 and so on. So for example, this works when X is any complete intersection. So any complete intersection is going to be a Cohen-Macaulay. And so this gives you a way to, actually local complete intersection. Sorry, it doesn't have to be global complete intersection. This gives you some way of understanding dualizing sheaf. And in particular, in this case, when the dualizing complex is just concentrated in 1 degree, then the third duality takes form very similar to the case of smooth varieties. So dualizing complex in that case is just going to be this sheaf in degree, so shifted by dimension of X. So if so the version of for X Cohen-Macaulay pure dimension n, the dualizing sheaf, so the dualizing complex is just going to be omega x shifted by n, where this one this one is no longer a line bundle as in the smooth case, but it's some coherent sheaf. And so the third duality would look like this, that if you take Hi, the kind of classical third duality, this is dual to x n minus I from f to omega x. Okay, so unfortunately I ran out of time, so maybe so I wanted to do some computation of derived restriction for the closed embedding, but maybe we'll do it. We can do it like during the discussion session a little bit, yeah. Because are you going to need it tomorrow?
Oh, I could do it tomorrow.
Yeah, or you could do it tomorrow. Okay. Yeah, and so now we have to go to this barbecue. Hopefully it's not raining.